All right, so this first one is using nodal analysis. Remember I said when we're doing nodal, first thing we need to do is label our nodes. So here's a node, and here's a node. There's other ways if you wanted to label it as far as like following the line around, that would also work. But this is ground, and the voltage at ground is 0 volts. And that's also called the reference node. It was given right here. That's what this symbol is ground. We'll call, oh, maybe someone was asking what is VA. Maybe that's what wasn't clear. So this one is A right here. If you solved it for the other one, then we probably, I'll look at the grading if you solved it for this other node, because that one doesn't really take any solving, because we'll call this VB, and it is 5 volts. The reason we know it's 5 volts is because there's a 5 volt voltage source right here, following up, goes up through 5 volts, and this entire node has 5 volts throughout it. So we're going to use nodal analysis to determine VA if our load is 100 ohms. So we can also set this to 100 ohms. So using nodal analysis, the next step, we have our node voltages, and we're going to do currents. I'll draw this one going in, this one coming out, and this one coming out. I think this one was called I load, right? So to use nodal analysis to determine VA if our load equals 100. So what goes in must come out, according to Kirchhoff's current law. So the sum of the currents in equals the sum of the currents out. I have I1, I2, we'll call that I load. Going in is I1, coming out is I2 plus I load. So now we can solve Ohm's law, or put Ohm's law for each of these currents. I1 is going from B to A, 5 volts minus VA, VA is unknown, going across 300 ohms. I2 is going from VA down to ground, so minus 0 or just VA over 500 ohms. All we're using here is we're using Ohm's law of V over R, right, for each element. We're saying across the 300 ohm resistor, there's current going through it, there's a voltage across it, its voltage is 5 minus VA. The voltage across the 500 ohm resistor is VA minus 0. And then I load is going from VA down to ground, going across 100 ohms, because they said our load was equal to 100 ohms. So there's my 3 parts. I can plug them all in. 5 minus VA over 300. Plug I2 in, VA over 500. Plug I load in plus VA over 100. So from here, you could use numsolve on your TI-36X, which is right above the sign button on the calculator. Second sign would give you second numsolve. You can just plug all these in using VA as X. You could also do it by math, and it's not too bad, this whole one doing it by math. Least common denominator of 300, 500, and 100 would be 1500. So what that turns into is 5. 15 divided by 3 is 5. 5 minus VA. 1500 divided by 500 would be 3 VA. 1500 divided by 100 would be 15 VA. So if you did this one by hand, it also works. 5 VA, 3 VA plus 15 VA. I can pull that one across, and I have 3 plus 15 plus 5. All of that is VA. And over here, VA is equal to 25 divided by 23, which comes out to 1.087 volts. Now we can do the power dissipated by the 100 ohm load resistor. Power, we have multiple formulas for it, but we could do I squared R. We could also do V squared over R. We could also use P equals VI. The one that you have readily available, so the fastest one would be the V squared over R, because the P load is equal to V load squared divided by R load. Well, that is this number right here, because V load is the voltage across the load resistor, which is VA to ground. So the single subscript just means relative to ground. VA is relative to ground, which is the V load, which we just solved for. So I could plug that in. 1.087 squared divided by 100, and I get 11.815 milliwatts. So there's the first problem on the quiz. Any questions on that before I move on to the Thevenin? Nope. All
Sure.
right. Yep, go ahead.
Just real quick. So if you got the first part wrong, but got B right, you just used the wrong value. Will you give partial or full credit for that one?
I get full credit. And
Okay.
You'll see me grade, I'll write ECF. That means error carried forward. So,
okay.
And sometimes if you get stuck, because some of our problems will be multi-part. So if you have 4 parts of a problem, and you're just truly stuck on like number 2, at some point, maybe not immediately, don't just start assuming values because you would like to solve for it. But if you just assume a value to be able to solve for parts 3 and 4, that would be better than not completing.
Thank you, sir.
Yep. So if you get stuck on this, and you're like, oh, I know how to do power. I have no idea what this voltage is, but I know it's V squared over R. Call VA 1 volt, you know? And you write, like I said, always write your assumptions down. So this one is the same problem, actually. 200, 5 volts, same problem, and it's the same circuit. We're going to solve it using a different method, 500. And then what it calls it right here is a 100 ohm load resistor. So once again, our load is equal to 100 ohms. So if you recognize that and you solve for one of these wrong, but you wrote, these should be the same because I'm going to solve for them the same, that would be a good way to get partial credit as well. If you recognize that this was the same problem as up above as far as the circuit goes, just a different method of getting to the answer, right? So whenever we do these Thevenin equivalents, I always say whenever you see Thevenin, think I can do it. And what that means is you're saying, I can take a complicated circuit and I can make it look like an easy circuit. The easy circuit being this one right here, right there, and I'll call this our load. This is our Thevenin that we'll be solving for, and this is E Thevenin that we'll be solving for. So Thevenin means I can do it. I can take, no matter how complicated it is, I can make it look easy. I can make it look like this. And how do I do that? I do 2 different methods. One for R Thevenin, one for E Thevenin. E Thevenin, we're looking for a voltage. R Thevenin, we're looking for a resistance in ohms, right? So I said it's often helpful to redraw, so I'll draw this part in blue now. So here's my E Thevenin circuit. Is I leave everything in place. The only thing different is I remove the load. And right here, nodes A and nodes B, I'm looking for the voltage between node A and node B, which is this node and this node. Okay. Thinking back to how the voltage works, this was 5 volts. So this node right here, there's 5 volts there. And I'll draw it in yellow, but it takes a drop here and it takes a drop here. All right, we got up to 5 volts, it goes down, it goes down. How does it go down? Well, if we follow to the right from 5 volts, it goes down through 300 ohms and down through 500 ohms. Well, those two are in series, so we can use series shortcut, series, which is voltage divider rule. The voltage divider rule is Vx equals Veq, Rx over Req. The X in this case is we're looking from A to B, which is this 500 ohms. So the Rx is the 500 ohms. The voltage being shared between the two series elements that are highlighted in yellow, right? The voltage being shared is 5 volts, and the equivalent of those two is 500 and 300, which would, I'll just go ahead and write as 800, right? That is my voltage from A to B. My R from A to B was 500, and my voltage in total going from the 5 volts down to 0, right? That was 800, went through 300, went through 500 ohms. Together that comes out to 3.125 volts. So E Thevenin is equal to 3.125 volts. Now for the R Thevenin, it's helpful to redraw. It's especially helpful to redraw. You don't need to redraw the E Thevenin if you don't want to. R Thevenin, I highly recommend it, and we'll actually see this one especially why that works out better. So I have my circuit, and I remove the load, and then I zero the source. The source was going right here, and so it is a wire now. It is a short, 0 voltage. There's no voltage drop across that. And what we're looking for, I'll label the nodes in green again, we're looking for the voltage, or sorry, the resistance total going from A to B. Now here is what B was initially, but now that we've added in a wire, I'm going to redraw my node. I drew it there because that's probably what you're thinking of, and that works. But this is also all a part of node B, because there is no, notice there's no elements inside of that entire set, right? So that is the true node according to how we draw nodes. And so for the ohms to get from node A to node B, it is only taking the 300 in parallel with the 500. These on the left are essentially dead. They're not plugged in where they're receiving current. And that's the point of a short, which is why I say don't let your body become a short, right? If the circuitry is over here and you connect with your two hands across two hot wires, you could become the short. You're the path of least resistance, right? So if you didn't see that node, another way to think about it is rather than that entire node, if you did have it labeled this way, would be to imagine the current coming through the 300 ohm resistor, and then it wants to go 3 different ways, but it takes the path of least resistance, right? And so when it takes the path of least resistance, nothing is going through the other two. It's all going through the short. So if you follow the nodes, that's my preferred way to do it, like that. All right, and these are dead. So 300 paralleled with 500 gives me 187.5 ohms. Right here, 187.5 ohms. And that's, so it says solve for and draw the Thevenin equivalent circuit. So that is what we did right now. Here's our solution. This is what you would box if you were boxing your answer. I've drawn my I've solved for and drawn my Thevenin equivalent by solving for E Thevenin and solving for R Thevenin. Now we're going to find the current flowing through a 100 load resistor connected to the Thevenin equivalent. So all that this is saying is that inside this circuit, this is 187.5. This is 100, 3.125. So we wanted the current flowing through it. Well, this is a series circuit, so all the current's the same. So I'll call it I total, V total over R total. Well, my V total is 3.125 volts. My R total is 187.5 plus 100. And that comes out to 10.87 milliamps. That is I total, which is also the I load, because it's a series circuit. They all have the same current flowing through. The question is the power used by that? Well, this one, going back to the idea of the fastest way to solve it, there are 3 different formulas. P equals I squared R, P equals VI, P equals V squared over R, but we already know I, so I'm going to use that one. 10.87 milliamps squared times 100, because I'm looking for P load, which is I load, R load. Those are all the ones that get plugged in together, and I get 11.815 milliwatts, which makes sense because it was the same circuit. If I had a 100 ohm resistor, I also had 11.85 milliwatts whenever I was looking at it with Nodal. It's the same circuit. If I plug in 100 ohms, I'll get the same solution. The last one is the maximum power that could be transferred. So when our load is set equal to our Thevenin, then the maximum power equation is occurred. So I could use the shortcut and say V Thevenin squared over 4R Thevenin. That would be 3.125 volts squared over 4 times 187.5. And that gives me 13.02 milliwatts. Say that you didn't want to use the shortcut formula, but you knew that our load had to equal our Thevenin. Well, essentially what you're doing is you would say I squared, right? This is the other way to solve it. The maximum that P load could be, I load, R load. Well, now I would have to solve for my I load again, right? I load would be 3.125, 187.5 plus 187.5, and then I would plug that in with using 187.5 because that's my new value that I've set. And if I did all that, I would also get 13.02 milliwatts. Try to stop the